Hello, today we're going to take a look at the solution to problem number 22 in chapter 11. So basically what it asks you to do is prove that the angular momentum of an object at the end of moving in a conic pendulum style problem. They want you to prove that it is, instead of saying it, let me just show it to you. So straighten that up a little bit. So I want you to prove that it's m squared g L cubed sine to the fourth theta over cosine of theta, the whole thing square root. So the question is, how do we get to that? Okay. So I have a whiteboard here in case we need it, but I think we're just going to take what I did on the solution here. Let me get this flattened out. Okay, so the basic idea is that we have an object on a string moving in a conical pendulum. The string length is a length L. You'll see over here I started to use capital L and I realized capital L is angular momentum, so that's not a good idea. So I switched to using lowercase cursive l, if you will. And I realized that the length of this string creates a radius of a circle as this conic pendulum goes around. So I just am getting ready that r is L sine of theta, okay, the theta being the angle created with the vertical. And then I started thinking, okay, well, what is angular momentum? Angular momentum is r cross p, and so that'd be r mv sine of 90 because r and v are perpendicular to each other. See, as this thing moves around in a circle, the velocity is tangent to the circle, and the radius is then perpendicular to the velocity. So they want us to prove this. I like to write it with a square root, but to the half power is the same thing. So I'm going to start by taking my radius equivalent thing, L sine of theta, and I'm going to plug it in right here. So if I just go from this step down to here, and so I get L, the angular momentum, is mv lowercase l, the length of the string, sine of theta. But that's not the answer because that's not what it looks like. I need to get rid of v. That's a big one, get rid of v. So I started thinking, what is v in this case? Well, v, once again, is perpendicular to r. So that makes it the velocity in a circle. So things like AR is v squared over r. Force radial is mv squared over r. These are all the same v. So I started thinking, well, I need to bring in sine and cosine of theta again, because we have a sine to the fourth and a cosine of theta. So I started thinking, why don't we try our old, what was that, chapter 6? Way of looking at a conic pendulum. So if you look down here, we've got tension and gravity, but that tension splits up into partly vertical and partly radial. So I did a sum of forces vertical, and I get T is mg over cosine of theta, and then a sum of forces radial, and there is only one, sine of theta, and that's mv squared over r. Go to the second page here. So on the second page, there we go. On the second page, I wrote what we found in the radial force here. That's what we had from sum of forces vertical, so I'm just plugging it in. And then you can see sine of theta, cosine of theta becomes tangent. The m's cancel here. And so you end up getting v is the square root of gr tangent of theta, something we've seen before. Now I realized at this point, maybe I shouldn't have used tangent of theta because the problem has sine over cosine. So I put a little note here. I should probably switch back at the end to sine of theta over cosine of theta. All right, so we had this from the beginning. I just figured this out, so let's plug velocity into there. And then I need to turn this into the final result. So I noticed the final result, everything's in a square root. So instead of m outside of the square root, I made it m squared inside the square root. Same with L, same with sine of theta. G and R were already there, and then you can see I did the sine of theta over cosine of theta instead. And since we know r is still L sine of theta, if I plug that in right here and simplify all this out, we finally get to the answer. So I hope that helps. That's how I plugged everything in and got to the answer they're looking for. See you next time.